Hello everyone, I'm Vincent Schoonderwood from Scientific Volume Imaging, the makers of the Huygens software, and I'd like to present to you today a webinar on LowSignal, on making imaging compromises and using Huygens. Many microscopists are struggling with low signal samples, so difficult to image. Take for example here this confocal dataset from Leica SP5. It has a signal to noise ratio of 2 in the green channel and 14 in the blue channel, which is quite low. Likewise, images that suffer from light decay in time are difficult to image. And you see that here in this mitochondrial movie, and on the right side you see our bleaching corrector, and you see that the decline in signal over time. So you need to make trade-offs during imaging. So you're confronted during image acquisition with this pyramid of frustration. And this was adapted from LowSignal et al. From Nature Methods. So you need to decide between contrast, temporal resolution, so sampling in time, sample health, phototoxicity bleaching issues, and spatial resolution. For example, if we add more light during acquisition to improve the contrast and improve the temporal resolution, so we are more able then to image faster, we compromise the sample health. So there will be probably more phototoxicity and the image will also suffer more from bleaching. Also, if we decide for shorter exposure times because we want to image faster and we want to keep our sample health more healthy, then we have a problem with contrast. We have less signal. If we decide for longer time intervals, so still imaging long enough to get some signal, some contrast, but image with frames with more time in between, also to save the sample itself, then we have a problem that the temporal resolution may not be enough, so we may miss fast events in time. So what now if we could improve the signal to noise ratio to quite an extent, and also that spatial resolution, and with that we have more flexibility in setting the sides of this pyramid. And this technique is of course called deconvolution. So if we deconvolve and improve the signal to noise ratio significantly and the resolution, we can push the boundaries of this pyramid. So we just need to accept lower signal and perform a deconvolution on top of that. Just some examples. This is a wide field dataset from Alexia Varant. On the left side the raw dataset, and on the right side the Huygens deconvolved. And if we make a line profile through the centrosomes, we see that the signal improves significantly. This is like 20 to 30 times higher. And also with that you see that the resolution of the objects improve, and you see the donut structure of these centrosomes. Another example here is from STAT, neuromuscular junctions imaged. You see here the raw data and the deconvolved version. If we take two details of that, two zooms, and place them here, and the deconvolved versions at the bottom, making line profiles through that, then we see here the intensity plots. The intensity increased more than 8 times, and the resolution also increased more than 1.5 to 2 times. So by having such a high signal gain, we have much more flexibility in setting the sides of this pyramid of frustration. So let's just now make a step back and look really at what happens to an image. So if we image a sample with a microscope, fluorescent microscope, this image is suffering from background, diffraction and noise. There can be more artifacts of course, but let's just now focus on these three. With deconvolution we can improve the background, we can control for the diffraction, we can correct for that, and we can deal with the noise. And we do that partially with the point spread function. So the point spread function is a model of how your point source object is diffracted, and we use this point spread function to improve the image and to increase the contrast. Then there are point spread functions for every different microscope type. So every microscope type has its own point spread function. And we support all these systems. So almost any microscope. Then the files that are saved often include the metadata, and we read the metadata from many different files, and we read that in our microscopy parameter editor, and you can edit them and optimize them further. And this allows us to create an optimal point spread function model. So now to noise. Noise is a function of, so the signal to noise ratio is a function of the square root of the number of photons. So the more signal you have, the less problems you have with the noise. And this is nicely indicated here in these panels. Every panel has a 10-fold increase in the number of photons. And you see that the contribution of noise, which is prominent in the first panel, where you actually don't see really objects, it's only noise. The contribution of photons to the buildup of the object improves then with lowering or increasing the signal to noise ratio. So we control for this signal to noise. Huygens estimates the signal to noise from the photon statistics. It sets it in the deconvolution wizard, so you're presented with the calculated SNR value, and with the AcuT mode. This is now a new mode in the most recent software versions of Huygens. You can further smoothen and sharpen the image. You can overrule the setting of the SNR value if you like to, but the AcuT setting should on a good acquired images should do the job. So here an example of that. This is a raw confocal data set from a Leica microscope. It has a pixel range value from 0 to 63, so not a lot of photons captured. The mean pixel value is 0.7. And here we see that by using the slider to the left, pushing it to the left, we get a smoother result with deconvolution. In the center, there's the automated Huygens setting, and this gives a great result. And in the middle, at the right, we see a sharper image, and this can create some noise enhancement. So you should be careful with this. But the default settings here, the automated settings, are fine. Now background, the third factor. Background needs to be corrected for. And why is that? Well, consider these three objects. They have a different amount of signal in them, and that has been imaged. Let's suppose of the green object we measure 100 as a signal, the blue 40 and the red 110. If we set the offset now higher during acquisition, we measure different values, and these values have a completely different ratio if you compare that to these values. So if you do any measurements, comparisons between intensities between objects, that is masked by the offset setting here. So you should subtract the background setting, that offset setting. So with high photon count, noise is not so much of a problem. So noise is here now inserted as these black spikes. But with low photon count, we also have lower signal, and the noise becomes more prominent. We have much more difficulty distinguishing between what is noise and what is real signal. So then the setting of background becomes really crucial. So a slight difference in the background setting will have already a huge effect in distinguishing between signal, or what is signal and what is no signal. So we determine the background from the image very specifically. So from a wide field image we look at the focal plane, and from non-wide field images we look into the whole 3D stack. And we create spheres of 0.7 micron, and from these spheres we apply a Gaussian filter to that, and from that we determine the background value. So Huygens calculates this background value again in the wizard, but also in our other tools. And you can set this into different modes. We have a wide field mode, so that looks then at in the focal plane. We have a lowest mode that is by default in non-wide field images, and we have an in-near object mode, and this you can select if you want to. So then you assume probably that the background is higher, closer to your object of interest. And if we hit now the button auto, then Huygens will come up with the optimized background value, and you can check that in our software. And of course you can enter values also manually. So let's now look at an example again. This is a raw confocal dataset, again from a Leica confocal, an SP8. And here we used different background values, 0.05, 0.01, and we used the Huygens automated mode. And you see that it comes up with a value that I would at least not guess. And you see the effect of that. The automated mode still shows objects that disappear if we use a too high background setting. So of course you can set it manually and lower it manually, but Huygens gives already a very good suggestion in what the background value should be. So Huygens not only improves the contrast, but also the resolution, even from low signal data. And here I want to make a point, is that if you use high line averaging, so sample the image 16 times with lines scanning and average that signal, then you get a result with a high SNR setting in Huygens that looks like this. But the 2 times line averaging isn't that worse. So if you have a lot of low signal, or if you have low signal, it is of no problem if you use Huygens deconvolution after that. There is, however, a problem with averaging. So with low signal data, it is much better to use photon counting mode or accumulation mode. Because if you look at the Poisson statistics, then the contribution of noise with low signal is very high as compared to more signal, but also there you can have a rounding problem. And this rounding problem in fact removes signal. The same is with if you do averaging. Suppose if you average 8 times a pixel signal of 1, 0, 1, 0, 0, 1, 0, 0, 1, 0. Those are the photons that you captured in this pixel 8 times. You divide that by 8 and you end up with no photons. So we've effectively lost 3 photons here during the acquisition. The photon statistics are really then messed up, and the result will also not be good. So you lost information already in your raw data, but also after deconvolution. And this is also nicely reflected in this histogram. If you apply no averaging, you still see that you have a lot of signal or reasonable signal here, but you lose this signal if you average more. So it's not a good idea to average at low signal. So some suggestions then. So the background, if they're really low, the correct estimation is crucial, and use photon counting detectors or use accumulation settings. So you have non-linearity of single photon events, and that can cause a disappearance of weak objects. So be very careful then with the averaging. Then also very important, use Nyquist rate sampling. Many of you know already, some of you may not. We have a free svi.nl Nyquist calculator website. Just consult this before you start imaging. The priority is really sampling. Remember, again and again, Huygens improves the signal, so stick with the sampling. We also have a Nyquist app for Android. Here you can also consult what the ideal Nyquist rate should be. So you can install it on your phone and take it with you if you're allowed to the imaging room. The exception to this is ray detector image deconvolution of Huygens with the Super XY and Super Y mode. The Super Y mode is then for fast area scan images. Here we can kind of undersample the data, so using larger pixel sizes, and with deconvolution we can decrease the pixel size. So how does this work? Suppose we have here a Gataquant nano ruler with 2 fluorophores at the end of similar color, one of a different color in between. They're 140 nanometer spaced, so 17 nanometer and 17 nanometer, that's the one in the middle. We take a raw image, and we see here the blurred version with the pixels projected on top of it. With conventional deconvolution, we would not be able to separate these fluorophores, but with Huygens Super XY deconvolution, where we decrease the pixel sizes, we supersample the data, we can efficiently separate these fluorophores. And we measured this for real, and what we can do, separate is 17 nanometer spacing between 2 different fluorophores. So this is all thanks to Christopher Lagerholm, who provided these images. And an example of Super Y deconvolution of size fast area scan data. We use the relative positions of the image and of course the intensities. And if we look at neurons before and after deconvolution with Super XY, we see that we nicely resolve the neurons with the dendritic spines. And this is thanks to Giovanna Esposito. So more on area scan deconvolution will be in the next webinar that is soon broadcasted. So at the end, I invite you to try Huygens yourself. Think about lowering the signal when you're acquiring the image. Keep the sampling as is, so according to our standard. Deconvolve and then see what you get. So judge the image after deconvolution. You can request licenses on our website, trial licenses, and yeah, we hope to hear from you. Bye bye and thanks for watching.